In class activity 2, for the following electrical network, derive the state equations and draw the block diagrams that represents the plant. Assume that the input is U of t and the output is either I of t or V of t. We'll see how that changes the final answer. Note that I'm marking the polarity on V of t here, positive on top, negative on the bottom. So we will select our first state, x1, to equal V of t, and our second state, x2, to equal I of t. So first, our KVL equation, U of t is equal to I of t times R plus L di of t dt plus V of t. Our second equation is that I of t is equal to C dV of t dt. So now, when we make a substitution using our state definitions, we get that U of t is equal to x2 times R plus L times x2 dot plus x1. In our second equation, we get that x2 is equal to C x1 dot. So our next job is to solve for x1 dot and x2 dot. x1 dot is equal to 1 over C x2. x2 dot is equal to negative 1 over L x1 minus R over L x2 plus 1 over L U. So now what about our output? Since we have two possible outputs, one of them is Y of t is equal to V of t. So that would mean that Y of t is equal to x1. Or our other option was Y of t is equal to I of t. And that would mean that Y of t equals x2. So now let's draw our matrix equations. So the system equations are x dot, which equals x1 dot and x2 dot, is equal to 0, 1 over C, negative 1 over L, negative R over L, times x1, x2, plus 0, 1 over L, U. And if Y is equal to x1, then the C matrix is 1, 0 times x1, x2. Or if Y is equal to x2, the equation is Y is equal to the C matrix, which is 0, 1 times x1, x2. So now let's create the system block diagram. We have our input U of t, and that goes through a summer where this is positive, and then we're going to have two negative inputs. This line down here is x1, and this line here is going to be R times x2. So then the output right here would be U minus x1 minus R x2, which we multiply by 1 over L. The output is x2 dot, and then we integrate by multiplying by 1 over S, and the output is x2. So now we multiply x2 by 1 over C, and the output is x1 dot. We integrate x1 dot by multiplying by 1 over S, and we get x1, which connects back to here. And then the output, Y of t is equal to x1 for this first equation, or if Y of t is equal to x2, which is the second equation, then we would show y of t right here. For the following electrical network, derive the state equations and draw the block diagram that represents the plant. Assume that the input is u of t and the output is I naught of t. So as usual, the first thing we're going to do is to assign the states. So we're going to let x1 equal IL and x2 equal VC. And now we're going to write a KCL equation at the top node where this is labeled ground. And the KCL equation is U of t equals VC over R plus IL plus C dVC dt. And that's our first equation. Our second equation is going to be a relationship between VC and the voltage across the inductor. So VC is equal to L DIL dt. Now we can rewrite these equations in terms of the state equations. So equation 1 would be U of t is equal to x2 over r plus x1 plus c x2 dot. And equation 2 would be x2 equals L times x1 dot. And since the output is I naught, y is equal to I naught, which equals VC over R. So y is equal to x2 over r. So solving for x1 dot is equal to 1 over L times x2. And then solving for x2 dot is equal to negative 1 over c x1 minus 1 over rc x2 plus 1 over c u. And we already had that y is equal to 1 over r x2. So in matrix form, we have x dot, where x dot is a vector, is equal to 0, 1 over L, and that's times x1, x2. And the second row is negative 1 over c, negative 1 over rc, and that's negative 1 over c times x1 minus 1 over rc x2, plus we have 0, 1 over c times u, and y is equal to a 1 by 2 vector, that is 0, 1 over r x2. And the last thing we want to do is to create the block diagram. Finally, let's draw the block diagram. The input is u of t, and that goes into a summer that has 2 negative feedback lines. One of them is x1, and the other one is 1 over r x2. So we have a 1 over r here and x2 here. So the output right here is u minus x1 minus 1 over r x2. And we multiply that by 1 over c, and the output is x2 dot. We integrate x2 dot, and the output is x2, which connects to here. Then we multiply that by 1 over L, and the output is x1 dot. And we integrate x1 dot, and the output is x1, which connects back to here. Since y is equal to 1 over r x2, and this is x2 here, we tap off of the x2 line, multiply by 1 over r, and the output is y of t. And this concludes today's lecture on state space representation.